Good morning. It's September 25th, and this is your daily brief in science. Here's everything you need to know. Recent studies reveal a promising advancement in the fight against pathogens through the use of silver nanoparticles, or AGNPs. These particles have demonstrated significant antimicrobial activity against a range of pathogens, including Staphylococcus aureus, Escherichia coli, and Candida albicans. Notably, the incorporation of AGNPs into dental materials like composite resins and glass ionomer cements has enhanced their antibacterial properties, potentially extending their longevity. Nanotechnology is gaining traction as a viable method for developing effective anti-caries agents, but the review of current findings indicates a pressing need for more clinical trials. This is particularly crucial due to the variability observed across different studies. As antibiotic resistance continues to rise, there is an urgent demand for novel antimicrobial agents, with chitosan-based nanomaterials being highlighted for their potential use in wound care. Chitosan is recognized for its effectiveness as a green-reducing agent and stabilizer during the synthesis of nanoparticles, contributing to its antimicrobial applications. However, its effectiveness can be limited by solubility issues in neutral or alkaline environments, which researchers are addressing through various modifications. Moreover, recent research suggests that modified titanium dental implant surfaces may exhibit antimicrobial effects against bacteria linked to peri-implantitis. Various surface treatments, including physical, chemical, and electrochemical methods, have been explored to enhance the antimicrobial properties of titanium implants. Overall, these findings indicate that integrating innovative materials and methods in dental and wound care could significantly improve treatment outcomes and address ongoing health challenges. The continued exploration of antimicrobial agents is essential as we confront rising microbial threats. Astronomers have made a significant breakthrough in understanding the atmosphere of the exoplanet WASP-107b, using NASA's James Webb Space Telescope to identify atmospheric asymmetry. This discovery challenges previous models that suggested such exoplanets would not exhibit this phenomenon. Lead author Matthew Murphy from the University of Arizona pointed out the advantages of space observations over traditional ground-based methods, which have limitations in studying atmospheric conditions. Co-author Thomas Beatty highlighted the importance of directly observing these asymmetries through transmission spectroscopy from space, providing clearer insights into the planet's atmosphere. WASP-107b is a gas giant that is tidally locked, meaning it consistently shows the same face to its star. This results in a permanent day side and night side, making it an ideal candidate for atmospheric research. The planet, discovered in 2017, has a mass similar to Neptune but a size comparable to Jupiter, orbiting a cooler and less massive star than our Sun. The atmospheric temperature of WASP-107b reaches around 890 degrees Fahrenheit, placing it between the cooler planets in our solar system and the hottest known exoplanets. The detailed snapshots captured by the James Webb Space Telescope provided insights into the atmospheric gases, cloud structures, and overall chemistry of the planet. The findings were published in the journal Nature Astronomy on September 24, 2024, and add to our understanding of how exoplanets maintain their unique structures and climates. Further studies are planned to explore the causes of the observed atmospheric asymmetry, with modeling suggesting that local enhancements of CO2 may be due to cold traps that allow for CO2 adsorption. This raises questions about the origins of CO2 in the atmosphere, potentially stemming from the radiolysis of CO2 precursors or sputtering from H2O ice. Researchers have made significant advancements in the development of high-entropy alloy composite coatings using laser cladding technology. This innovative approach focuses on the cobalt, chromium, iron, manganese, nickel, zirconium dioxide alloy applied to martensitic stainless steel substrates. The laser cladding process refines the microstructure and achieves a uniform distribution of elements, which is essential for enhancing the mechanical properties of the coatings. The coatings consist of a transition layer and a hard surface layer, which features a high concentration of spherical tungsten carbide particles. The study emphasizes the optimization of tungsten carbide content in nickel-based coatings to find a balance between hardness and wear resistance. Notably, the iron-nickel-chromium combined with 3% niobium carbide coating demonstrated superior micromechanical properties, achieving an impressive average micro-hardness of 3.8 gigapascals. Tribological tests revealed significant improvements in wear resistance, with coatings containing titanium carbide and niobium carbide showing weight loss reductions of 37% and 41%, respectively. Furthermore, electrochemical tests indicated a marked enhancement in corrosion resistance for the composite coating compared to the substrate. Finite element simulations also highlighted that zirconium dioxide particles improve resistance to cavitation erosion by enduring higher stress and generating compressive stress on the coating surface. The results showed that adding zirconium dioxide increased the coating's micro-hardness, with the highest hardness of 348 Vickers hardness achieved at 10% zirconium dioxide content. Additionally, increased silicon carbide content was found to prolong the initial wear stage and lower the wear rate by delaying the breakdown of the oxide film. The ongoing demand for materials with superior performance in harsh environments is propelling the development of high-entropy alloys, particularly for applications in turbine blades and bearings. High-entropy alloys are characterized by unique properties arising from high entropy, lattice distortion, hysteresis diffusion, and the cocktail effect. A recent study has highlighted serious implications for astronauts' heart health during long-term space missions, particularly those aimed at Mars. Previous research had already indicated heart issues upon astronauts' return to Earth, and this study builds on those findings. Scientist Jonathan Tsui led the investigation by developing human-induced pluripotent stem cells into heart muscle cells, which were then placed on a flexible tissue chip to simulate heart contractions. These heart tissues were sent to the International Space Station aboard the SpaceX CRS-20 mission in March 2020, where they were monitored for contraction strength and irregular beating patterns. Real-time monitoring enabled scientists on Earth to receive data on tissue contractions every 30 minutes, allowing for detailed insights into the health of the samples. As the experiment progressed, irregular beating patterns emerged, with a notable increase in the interval between beats by day 19. Microscopic examination of the space samples revealed disordered protein strands and swollen mitochondria, indicating deterioration compared to samples kept on Earth. Additionally, the study found that key structural components of the heart muscle, known as sarcomeres, became disordered and shorter, suggesting potential heart disease. Overall, the findings indicated that the heart tissue weakened, exhibited irregular beating patterns, and underwent genetic changes similar to those seen in aging. The research team, led by Tsui, continued to maintain and collect data from the tissues after their return to Earth. The results of this significant study were published in the Proceedings of the National Academy of Sciences on September 24, 2024, emphasizing the urgent need to understand the effects of weightlessness on heart function. Led by Deok Ho Kim, the research team included experts from multiple institutions, underscoring the collaborative effort to investigate cardiovascular health in space. Ongoing research aims to not only understand the impacts of space travel on heart health, but also to identify drugs that could help maintain heart function in aging populations. A citizen-led initiative has made significant strides in understanding microplastic contamination along Germany's coastlines. The Microplastic Detective Project, which ran from September 2021 to November 2022, engaged the public in environmental monitoring, allowing volunteers to collect sand samples from 71 beaches along the North and Baltic Sea coasts. Researchers from the Alfred Wegener Institute gathered over 1,100 samples, totaling 2.2 tons of sand, through this year-long project. The focus was on larger microplastics, measuring between 1 and 5 millimeters, with 1,139 samples analyzed. Findings indicated that microplastics were present at 52 of the surveyed beaches, although the concentration of larger particles was lower than in previous studies. Notably, many smaller microplastic particles, which account for over 90% of microplastics in other research, were likely present but not analyzed. This suggests that actual contamination levels could be higher than reported. The study, published in Frontiers in Environmental Science, revealed concerning levels of microplastic pollution, with some locations containing up to 400,000 plastic particles in the sand. On average, the samples contained about 4 plastic particles per square meter, but contamination levels varied significantly by location. Biologist Melanie Bergman highlighted the need for stricter regulations based on these findings to manage plastic production and usage effectively. The OECD projects that global plastic production could nearly triple by 2060, which would exacerbate microplastic pollution and potentially harm marine ecosystems. Standardized methods for assessing plastic pollution were deemed essential for evaluating the effectiveness of political measures aimed at reducing it. The success of the project was celebrated, with researchers impressed by the enthusiasm and dedication of the citizen scientists involved in the sampling efforts. This has been your Daily Brief in Science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. Tune in tomorrow. We'll be back with everything you need to know.